conference, which is a Brazilian computer science, computer architecture conference. It's always nice to be back here. Very well organized conferences and to meet all the researchers in Latin America. So today I will talk about some work we've been doing in accelerating GNNs, which is a very important machine learning model that's very popular these days, used in many systems, including recommendation systems, for example. And our focus here is to use a heterogeneous platform, CPUs, and multiple FPGAs. These problems are very large. We need to use multiple devices to get acceleration. So our focus here is that if you have a data center node with these kinds of accelerators, how do we kind of scale the performance as you increase the number of FPGAs in those systems, and what kind of data distribution problems, sampling problems that come in that context. Joint work with my PhD students that are going to be graduating, available for jobs next year or the year following. So what I have done here is to just to initially give some background on FPGAs. I'm not sure if all the audience here would know about it. I'll also spend some time on giving some context about what are the various graph machine learning models. There are various models in the literature here. I'll speak a little bit about it. And most of my talk is going to be focused on what are the challenges in accelerating and how do we effectively use these kinds of heterogeneous platforms to get high performance in these kinds of accelerations. And then also put some thoughts here in terms of there is quite a bit of interest here between the machine learning community and the architecture communities to understand is it possible to co-design these kinds of architectures so that I don't spend a lot of time here using various technologies to accelerate these kinds of models, which have been typically designed kind of de-linked from the architecture, so that could give some opportunities for a kind of a co-design here between machine learning and the parallel computing communities. So FPGAs very, very quickly, a large number of configurable logic blocks here that you can program them. You can, for example, program them to have a particular, let's say in this example, a 4 input function, 2 to the power 4 combinations that is kind of fused into the local memory you have on the particular lookup table you have here. Large amount of on-chip routing resources are available. So you can essentially configure this device based on your interest into particular kind of functions you want to compute, interconnections between them, and also there is quite a bit of static RAM on these devices available here, distributed static RAM, which can also be used for example, caching purposes if you're looking at GNN training that you're doing here. Very important to notice here, very high on-chip bandwidth, which we are going to be exploiting here in our implementations to get high performance GNN training on these architectures. So I call this as FPGA++. There is almost 30 years of research, hardware research in this space, where these devices are quite a bit significantly advanced at this time. So if you look at a modern device in the market today produced by AMD or Intel, they have quite a bit of on-chip resources, static RAMs, also what is called hard IP that is integrated into these devices. You can get, say, 16-bit multipliers, IEEE floating point multipliers, single precision multipliers, or variable precision arithmetic is available. Quite a bit of high bandwidth memory is available, just like in the GPU cases you have. A number of external memory interfaces are available here. So these devices are quite powerful. In fact, if you see in the market today, these devices are, in terms of the density that you have, the number of transistors you have, the kind of bandwidth you have on these devices, the number of floating point units you have on these devices. I'm just showing here 2 different state-of-the-art devices, a Xilinx device and an Intel device here. These are comparable to what you can get in a typical GPU device in the market today. That's kind of where this technology is advanced over the last 25 years. And so I think what we are focused here is that if you have these kinds of devices, multiple of those devices, how do we effectively use them for these kinds of machine learning applications and then get high performance by integrating them into a CPU plus a multi-FPGA platform. So I'm just comparing here the various devices in the market, looking at the FPGAs in the market, state-of-the-art devices, the multi-core platforms here, the GPU here, and also looking at one of the state-of-the-art accelerators that is coming up in the market, which is a very large accelerator in the market today. So I'm comparing them with respect to various performance metrics here. I won't go through the complete table here. The important message here is that these FPGA devices are comparable in performance in terms of, let's say, number of floating point operations per second you can do on these devices. There are quite a bit of performance that you can get out of these devices by looking at the amount of cheap memory that is available to us. This is a very large device here. This is like having something like 1.2 trillion transistors on this complete device here. This is a very large device. So if you compare the multi-core FPGA and the GPUs, these FPGA devices are a very good kind of alternate device to use as far as getting performance out of these devices is concerned. And very high peak performance on these devices, FPGAs here, in terms of teraops or teraflops per second that you can execute on these devices. There's quite a bit of opportunity here in terms of getting high performance on these devices. But keep in mind that these architectures are not like the programmable architectures here, that you have to actually devise the complete virtual overlay architecture on top of this FPGA device here, so that you have the full control over what is the architecture you want to implement on that device, and that architecture is the one that will execute your GNN training for us here. There's quite a bit of advances here in terms of how to specify those architectures on these devices compared to, for example, using Python or PyTorch, something like that, to be able to program the GPUs and the CPUs that you have here on the right hand. So there's quite a bit of device technologies as well as software tools available here so that you can get high performance very quickly by using these FPGA devices. So we have been doing significant work, I would say, in this context over the last several years. I've just listed some publications here, which is kind of leading us to this particular paper here in this conference, which is looking at how do we accelerate if we have CPU and multiple FPGAs in the device. The previous work here has been focused on developing new GNN models. These GNN models are kind of evolving over a long period of time in the last 15 years or so. And then we proposed various GNN models in these papers, and also looking at how do we accelerate those kinds of GNN models by using FPGAs and GPUs available in the market. So this particular paper, so what I'm presenting here today is focused here on looking at if you have a heterogeneous platform, we'll talk about why this would be useful for us, consisting of CPUs and multiple FPGAs, and how do we get high performance in those implementations. So given that background about FPGAs and the GNN importance, let's go a little bit more details of what's happening in the GNN computations and compare that against what happens in typical CNNs and DNNs, and see what are the opportunities for us to be able to use FPGAs to get acceleration and then actually come up with an implementation for that. So graph neural networks has been around for many years. In fact, many companies make use of that for their recommendation systems. It's a very widely studied topic area. The problem is very nicely simply defined here. We want to take this irregularly structured graph. Graphs are very large, and you want to embed each vertex is going to be associated with a vector. That is the mapping function we want to learn. That's what the graph neural networks training is doing for us to be able to understand how do you do this mapping from the nodes with features given to us, irregular large graphs, and then you want to embed that into a lower dimensional space. This could be typically 64 elements or 128 elements we have, and that's kind of the basic problem we are solving here as the training process here. So why it is important? If you can do this embedding here, essentially you have taken an irregularly structured problem and converted that into a nice problem in the vector space. And the large number of downstream applications that use classic problems here, you can solve those problems by looking at this vector space and doing operations. For example, you can do clustering, you can find nearest neighbors. So all those kinds of well-defined, very well-studied problems in the context of vector spaces using vector representations for inputs can be used to solve these problems, which are classic problems on graphs. So that's kind of is the connection between why GNNs are being used here to do that. So like I said earlier, Pinterest is just, and you might have already used this kind of software tools which use the graph neural networks for recommendation systems, and they do a lot of training. Training can be very expensive. These graphs are very large, looking at these graphs having tens of billions or maybe hundreds of billions of vertices and maybe trillions of edges in them. And then you want to be able to solve these kinds of problems, training as well as inference on these problems very quickly on these systems. Let's go a little bit deeper into it, the kind of problems we need to actually solve in this context. We're looking at the problem in which we're looking at this graph neural networks. I've defined the various parameters. There are a number of layers that you go through here from input to output. You sample the graph. Based on the graph, you create this adjacency matrix here and use that information for aggregation and then do the transformation here. And then you repeat this layer by layer. That's kind of what happens in the graph neural networks. If you compare that with the GNNs, these kinds of operations are all very structured. You apply maybe 3 by 3 or 5 by 5 windows in the case of CNNs. That kind of a structure is not available to us here. All this is, this connection that is shown here, that depends on the input graph. You sample the input graph, define this adjacency matrix here, and that matrix is used for the aggregation function here, and then you do a feature transformation here by looking at whatever is the feature vector you have in that particular layer and transform that into the next layer you have. That's kind of what happens in the systems. So if you look at the model representation, the model size here for the GNN, essentially this weight matrices layer by layer is what specifies this, plus the aggregation functions you are going to be using at the various layers. And you also specify what is the technique by which you generate this adjacency matrices you have for each layer. That kind of specifies different GNN models. There are literally tens of hundreds of different GNN models based on how this matrix is specified, what kind of aggregation you do here, and kind of what is the weight matrix that is given to you as part of the transformations you do in the going from input to output layer by layer. And the final last layer is the layer where we get the embedding vectors for all the inputs that is provided to the forward pass of the GNN matrix that we have. So I think if you look at it from our perspective, from the perspective of CPUs, GPUs, and FPGAs, what is the actual computation, what is the actual communication we do here to accelerate these kinds of computations? You're performing an aggregation function here, sparse dense matrix operations, and then you're doing a dense matrix operation, which is a transformation operation you're doing here. And then you apply this, whatever is the activation function that you apply at that point here. I've just made some notes here. These are really the notes from a perspective of parallel computing. What is the intrinsic challenges we have to address here to get high performance? This matrix that you see here is obtained by sampling the input graph we have. That's going to be a sparse matrix here. The weight transfer matrix is typically a dense matrix here. And the typical size depends on the number of elements you have in the vectors. In the feature vectors, you have the various layers. There's a typical size here. And then this particular size, input sample size here, typically in the range of 1K or so or 10K, and then each one consisting of 64 elements or up to 512 elements we have. That's kind of the big picture of what happens when you want to do these accelerations. At the back of your mind, you want to be always looking at this as how does this compare with what is the traditional techniques we have been doing for CNN acceleration. So we want to be kind of looking at those techniques and see if we can make use of them, given that the computations are different, and these matrices that are used here for different layers can be different based on the input graph, and that is a kind of the challenge we have in this context. So let me quickly go through it. The training here means that starting from the graph pre-processing here, you create various mini batches. You do the graph sampling here to create those adjacency matrices I talked about in the previous slide. Then you do the aggregation and transformation. You compute these loss functions here, synchronize all the processes, and then update those quantities you have, the weights you have, and then keep repeating this. I'll put this here as a main high-level program here. I put some question marks here. There is kind of a research here in this space. Should we synchronize all of those processes? There is various techniques to do that. And then what is the cost of updating this local copy of these weights you have here? I call this local copy here. So this is a difference compared to what happens in the context of CNNs. In the context of CNNs, when you talk about CNN training, you talk about a weight server, which kind of takes up quite a bit of your resources in the system in terms of communication. But keep in mind that the number of weights you have is very small in GNN. So this problem is not a problem as far as GNN training is concerned, compared with what happens in the context of CNN. So the kind of the overall flow is based on sampling and then updating, but there are significant differences compared to what happens in the context of CNNs. And what I did here is that let's take a typical GNN model and see where the real bottleneck is in those systems. What I'm showing here is for the execution time for each iteration. Various parameters are listed here. And I'm showing here for two different data sets here, for Reddit and Amazon data set here. What is the time spent in per iteration of this here? And the majority of the time here is spent in this step here in terms of doing this, looking at this adjacency matrix representation we have collecting all those features in that layer and then updating the features, the aggregation function that you're applying here, that takes most of the time. Okay, that's what is the kind of the bottom line here, that the DRAM accesses communicating between the FPGAs and the processor, where the real bottlenecks are. So if you can handle that problem, you can get high performance, scalable implementations for these kinds of applications. Very quickly here, I kind of touched upon this topic earlier. What is the difference between a GNN training versus the deep neural network training here? What are the differences that makes this problem different compared to what happens in the context of CNNs? The number of parameters in the model is small compared to what happens in the context of DNNs. The data size that you're using for sampling adjacency matrix representation comes, that's quite large compared to what happens in the context of DNNs here. And the kind of computations you do, communication you do here, I talked about this earlier. You have the sparse matrix computations coming into picture, irregular memory access patterns come. Compare this with the dense computations we do in the context of DNNs and very structured CN, the convolution operations you do here, which are not available in the context of GNNs. That makes this problem more challenging compared to what happens in the context of GNNs. So going back to our problem here, if you are using CPUs and multiple FPGAs, our challenges here are a large data size. They don't fit in the on-chip memory of those FPGA devices I talked about here. Large number of random memory accesses and very little data reuse that takes place in these implementations. Load imbalance, as you sample them, different adjacency matrices have different number of edges, different amount of work you do per iteration of the GNN model forward pass you have here. And the kernels we are using here, sparse and dense. If you do communication between those kernels to the external memory, that's quite expensive in these implementations. And also keep in mind that there are various input graphs, various GNN models. There's a large variation in those data sets you have in terms of sparsity, distribution of the degrees of the vertices you have here. That kind of makes this problem a very different space to work with compared to what happens in the context of typical computer vision models, so Bingyi 16 or 19, those kinds of models we have. I also put some more comments here. There's quite a bit of research in terms of what kind of sampling techniques to use. That also adds certain complexity into the way that you're going to be parallelizing it. The training is different from inference in the sense that latency is important, throughput is important here. Should I use the complete graph? There are quite a lot of discussion in the community, the machine learning community. Sampling is better or the full graph is better. There's quite a bit of ongoing research that kind of compares these various techniques. So let's go into why should we be using FPGAs. Really the focus of this paper is to look at if I have a multi-GPU platform and a multi-FPGA platform, what are the kind of trade-offs you have in terms of accelerating this here. We know about GPUs, we have the specific organization based on this data parallel programming model. I think the important advantages here is that you can have a customized memory access pattern. We have very high bandwidth on these devices that can be effectively used for those aggregation functions I talked about for GNN training here. And the memory organization can also be used here for us to be able to provide those sampled graphs on the device, which gives very high performance in those implementations. In all of these FPGA devices, you define this data path. You kind of structure this, use the high-level synthesis tools to be able to generate those data paths, and that gives us a very nice way by which, based on the GNN particular GNN model computations you are doing, we can implement those aggregate functions very efficiently on the FPGAs that gives very high performance in our implementations. So what we have done in this work, we are using the CPU portion here for us to do the graph pre-processing, the mini-batch sampling, all those are carried out on the CPU here. We are using various processor memory interaction connections, DDR channels, and the PCI Express for connections between the CPU and the FPGA. On the FPGA is where you have, there are multiple FPGAs we are using here on the PCI Express that is connecting the CPU and the multiple FPGA devices. And this is where we implement the various functions I talked about for each layer, aggregate kernel and the update kernel, sparse matrix here and dense matrix algebra here. And for that, we build a virtual overlay architecture on the FPGA and then initiate multiple of those architectures on each one of those FPGA devices we have. And then they are going to be working on the mini batches here that is provided from the CPU, and that kind of is the parallel activities that you initiate across those multiple FPGA devices you have. So there are a number of data communication issues come into picture. If you look at the complete workflow, we are doing the sampling on the CPU. And then when you do the sampling here, we have to take the sample graphs here, which is based on which you construct this GNN models based on the input graph and the sampling you did. And this is going to be distributed across the various CPUs, various FPGAs you have on the device. And then you compute the forward process and the gradients here, and then synchronize, and then you do the weight update here. That's what you do. Now this is not a problem. This is like I said earlier, this weight matrices that you are going from layer to layer. If we typically say we are probably exchanging about 1 million bytes of data here, so this is not a problem. This is a critical problem in the context of CNN. That's not a problem. The real problem lies here in terms of the sampling. These graphs are large. Irregular kind of data access comes into picture. That's where the CPU overload comes into picture. And when you do these sample graphs here and provide them as inputs to these multiple FPGAs, you have this load need not be balanced based on how these subgraphs look like here, and that's where the load imbalance problem comes into picture as far as the using multiple FPGAs connected to the CPU kind of a platform is used here. So our real problems are not on this side. This is what is a problem in the context of typical GNN training acceleration. So we are going to be focused here in terms of how do we deal with these kinds of mini batches which may have various amounts of workloads. And these mini batches may also be accessing from a particular FPGA to a different FPGA based on how the edges are distributed in the sample graph we have. So these are the kind of the challenging problems that we need to study in this context. So I talked about these communication problems are really the bottleneck here in terms of getting acceleration. The first challenge here is the kind of FPGA to FPGA communication that comes into picture. This problem comes because the input graph is partitioned across the various FPGA devices. When you sample them, a particular node may be resident on a particular FPGA device, but the edge may be connecting to the feature vector of a different node we have. And as I noted earlier, the amount of communication you do for exchanging the feature values is a critical overhead in the system here, and that's the kind of a problem that we need to solve here. We are using the METIS algorithm here for partitioning to reduce this cross edges that you have. That's a classic technique that is used in scientific computing that we make use of it here. So based on that, we create these mini batches, and then we kind of export them to the various FPGA devices to be able to do the operations in parallel. The second problem is the workload imbalance. I've just shown an example here. Different partitions, different sampled graphs will have different amounts of number of edges coming into picture. The number of edges is a measure of the workload on a particular layer you have in that GNN forward pass. And then so there is, we can do some simple scheduling here. As you are sampling, you can figure out the size of the graph that you are exporting to the FPGAs and use that information to work with the workload balance between the FPGAs that gives high performance in our implementations. Some experimental results. There are a number of results in the camera-ready paper that you can look into. What we have done here is that we have compared using a multi-GPU platform as the baseline here for NVIDIA A5000s. This is typically done by using PyTorch geometric as the tool that is used. We used the same tool here and then had a design flow to go from there to the AMD EPIC plus 4 Xilinx Alveo boards. The same number of boards. These are comparable devices in terms of the number of transistors, the amount of memory bandwidth you have, the external memory on these devices. What I'm showing here is for two different GNN models, classic models here. I'm comparing using the various metrics here, and I'm also showing here for the various data sets here, Amazon, Reddit, and the various data sets. And I'm showing here in the last column what is the geometric mean of the performance improvement we got here. Just if you look at, for example, the throughput here, throughput based on the iterations, what happens, I'm comparing the GPU here in terms of number of millions of vertices that you have per second. There is throughput here, and then compare this with what we are doing here, and then what kind of performance improvements we can get here in that context. I'm again comparing the graph convolutional networks, a classic model, and the graph sage model, which is also another classic model that is used, showing here the performance improvements we can get. So we performed these experiments by using 4 devices. That's what we could have access to in my lab. And I'm showing here scalability of these designs by using your performance model, looking at various data sets, and then as we increase the number of FPGAs, what is the throughput improvement that you can get in terms of scalability of this using multiple FPGA devices. So let me conclude by looking at some directions that the community is exploring that may be of interest to this community as well. I talked about GNN models. This is a very important, very widely researched topic area now. Various techniques, various GNN models being devised here. And these are the kind of performance metrics that is used here in the machine learning community in terms of accuracy, how good is in expressing the particular problem you're trying to solve. These kinds of GNN models are used to solve some combinatorially very difficult problems on graphs. For example, independent set problems, people solve by embedding them into a lower dimensional space and then doing some operations on that space here. So this is a terminology used by the machine learning community here. And from our community here, from the scientific computing, parallel computing, we are interested in these kinds of architectural and performance metrics here, how much memory, what kind of data reuse we have. And there is an emerging area of research here which is trying to bring these two communities together and see, should we be defining these models, which are complex GNN models here, by understanding what is feasible to implement on these architectures. Similarly here, how the architecture should be evolving here in terms of the requirements of this community here. So we are also involved in this. We are doing some work with Meta and Facebook in terms of defining these co-design frameworks and then how do we improve performance. Those of you interested, we had a paper at NeurIPS last year where we said maybe we should decouple the graph neural network models in terms of the number of layers, the sampling do here, and then use a different kind of samplers here. There is quite a lot of research in defining what are kind of attention mechanisms per node in terms of defining what is important for a particular node, what is the receptive field of a node. This is one of the work in that direction to understand how do we decouple the depth and the scope of the vertices you have so that you can get faster GNN models which have lower complexity in terms of execution on in these platforms you have. So let me stop here. Are there any questions?
Thank you.